Welcome to part two of Bridging the Cloud Divide. So during this session, we are going to be hearing from people who are using the cloud in practice. First of all, can you guys all see my screen okay? It has the introductory slide, Bridging the Cloud Divide. Okay, great.
Yep.
So welcome. So in the part one, we highlighted some technological advancements and some best practices for using the cloud. And so now we're going to be moving to, and if you missed any of that, of course, or want to review it, all of this will be recorded and posted, I believe on Zoom, or I'm sorry, on YouTube at some point, and Aaron can correct me if I'm wrong. So in this part two, I really wanted to, I really wanted to run with the theme of bridging the cloud divide by actually highlighting how the cloud is being used in practice to advance Earth science goals. So we're going to be hearing from a number of exciting projects. Rob is going to kick us off with talking about how CloudBank, which is a NSF-funded initiative, is providing cloud-based funding for researchers. Chad is going to follow that presentation with a project that actually used CloudBank, which is exciting, talking about a global scale database of seismic data. And then we're going to hear from Eliana Abrahams, who's going to be presenting Flip Inside, which is for prepping cloud Earth observation data for use with deep learning. Raphael is going to be talking about using COILD's collaborative environments at Carbon Plan. And then we're going to have a nice closing presentation from Puneet to talk about open data preservation using the cloud, and also the importance of community and culture in the adoption of cloud and really seeing it to its full benefit. And then if we have time, we'll have open Q&A. Before I pass it off to our first speaker, Rob, I'll just mention that you are welcome and encouraged to use the chat for asking questions. We can use that as a place to ask questions that especially we can't get to during the 50-minute window that each presenter has for their presentation. And if we have time, of course, we will ask those aloud as well. And then at the end of presentations, if we have a few minutes for questions, we will pause for those. So then you can use the raise hand feature if you would like to ask your question aloud. So with that, I think I will pass it off to our first speaker to kick us off is Rob Fatland.
Okay, so hopefully that worked. Worked a moment ago, so it must work now. Hello, everybody. Thank you, Amy. My name is Rob Fatland. I'm at the University of Washington, where I'm a research computing director. And I'm here to talk about CloudBank, which is commercial cloud access through this NSF-sponsored program that has now entered its phase two, CloudBank 2, where we have expanded our reach to all U.S. researchers and educators. So that's the TLDR of this presentation. And I'll try and keep things fairly short as I go through here. So from 2019 on to the present, we've had the CloudBank program running for 6 years, and that's a collaboration between UC San Diego and the Supercomputing Center there, and the University of Washington and UC Berkeley, supported by NSF, specifically the Computer Sciences Directorate. So this has been a very CS-oriented pilot. And the premise is that a research team can turn to the vast cloud computing power and other cloud resources, for example, databases and networking and access to AI models and so forth, and sort of use the cloud as a computing platform. But the question mark comes with the prospect of having a bunch of learning curves to deal with, and researchers don't necessarily have the time and the interest in doing that. And then, of course, the spend. So the question then becomes, is the cloud approach to research computing viable? And a quick answer, CloudBank has now supported something like 460 projects, that's individual research teams, with sort of an average spend of about $10,000 each. So we're seeing good evidence that this is in fact viable. So then we decided to, back when we were getting started, to run this experiment to answer this question, really with the philosophy of enabling entry path. And that means reducing costs. So we're dealing with that. We are helping researchers track their spend so that they understand the relationship between use of service and cost. We support learning cloud technology. That's mostly what I work on. So I'll be talking a bunch about that. And then we also brought in from Berkeley a data science curriculum, which sort of covers the pivot from doing the research to teaching. So the main important aspect of CloudBank in phase 2 is that we're now available through the NSF Access program. So that means anybody can come there. And I'll say more about that in a second. These are some quotes from researchers. When we were getting started, we wanted to sort of articulate what the perceived or real problems are. Time consuming, time to learn, billing is opaque, and so forth. So we've tried to adopt that. We've tried to address that, and we do that primarily by standing up a CloudBank portal, which is at cloudbank.org. So, as I said, then we sort of rolled forward 6 years to the point where now we are available through the Access program. So the next 2 slides sort of talk about that. You're eligible if you're a US-based researcher, educator, postdocs are eligible and so forth. And I'll let you just sort of scan through this. But the cost estimate justification with Cloud Vendor Calculator URLs, that's sort of a mouthful to unpack. But it just simply means if you want to use Access to get to CloudBank support, where you won't be paying dollars out of your budget, but in fact, you'll be using a pool of resources, then the first step is going to be to get on a cloud calculator. Each cloud provider has one of these, and you can use it to generate a spend estimate. And then we also have a help desk for CloudBank called help@cloudbank.org. So that's the sort of initial step. So to get going with Access, you'd do that calculator step on the far left there. Then you request an Access allocation. And then when you do that, you get credits, which then can be exchanged for CloudBank dollars. So there's some exchange rate. And the important point is then that once you get through this approval process, you're ready to onboard with CloudBank, and we try and make sure that you're actually ready to get into the cloud and start using it and tracking it. And so then we have these sort of 3 bullets over on the far right, which are to manage your users, presumably your team members, and your Access allocation. You need to be able to assign users to various cloud accounts, and we are agnostic. We have about 5 different clouds that we have access to. And then you start using resources, and hopefully you get back to focusing on your work, and the cloud becomes something in the rearview mirror that you figured out. So the Access program has these 3 different tiers that you can get into cloud credits with. And the average awards are, as you can see, 5, 20, and 60K. But you basically start off with this Explore tier, and then you can work your way up. And I've heard through the grapevine that this is not particularly onerous process. I'm going to take a moment to refer to something I said earlier, which is that Berkeley brings in an educational component. So Access also has a curriculum door that you can go through, and these slides will be available at the ESEP slide repository directory, so you can come back and find this link if it flashes by too quickly. But the point of the Berkeley program, which is based on a data science course called Data 8, is to provide a scalable Jupyter Hub environment that a bunch of students can use to start digging into data science. So that's the second paragraph here. I'll just read. It says, leveraging the power of the public cloud, we offer a consistent high-performance environment for students, regardless of their local hardware. And this is really an important aspect of cloud access that I'm strongly supportive of, which is that it democratizes access. If you can get into a program like this, then you don't have to come in with a massive budget to make use of these resources and these technologies. Okay, so the next few slides, I'll talk about cloud for research and specifically learning how to use the cloud. And to start that off, these are just sort of my thoughts on this topic. I'm at the University of Washington. I'm actually at the eScience Institute, which is focused on data science. And one of the things that we do is we have Hack Weeks, and somebody in the first session referred to ISAT2 as an example. And this is really steeped very much in the open science, open source culture. So that's what's kind of informing where I'm coming from. And so then, of course, as I noted, the cloud has compute resources available, GPUs, foundation models, and we have this data profusion. So this kind of leads to this idea of bringing your compute to the data. In other words, building your compute infrastructure on the cloud. And for every given team that wants to try this, there's a skill level that they collectively have. There's also the scale of the project that you want to attempt. And then there's your intention. Are you trying to write a paper? Are you trying to share a data set and so forth? So there's a lot of interesting dimensions to the process. And there are blockers, particularly the skill levels, and then optimization of cloud use. Plus, there's also not knowing what you don't know. So if you don't know what Flask is and you're trying to build a web app, how do you find out that? So we're trying to sort of build frameworks and communicate with our user base and to prospective users to enable them to sort of sail through these obstacles and get to a point where they're doing what they want to do in this gigantic workshop. And just two quick examples. In the cloud clinics that we give, I've talked about mounting a AWS S3 object storage bucket on a laptop. So it looks like your laptop suddenly has a 9 exabyte data drive that's mostly empty. You can learn how to use the Cloud Spot Market, which is preemptible instances that cost about 25% of the normal rate, and but there's some conditions that you have to learn about if you're going to operate on the spot market. So this is a slide about the Education Outreach and Training Cloud Bank resources, including a forum that we use for lifting up and documenting answers to common questions. There's learning resources that we're working on building an AI to help with. And then there's a Cloud Bank catalog, which is shown on this page. And I don't want you to read this fine print. It's just the idea that we can link to tools and services offered by the vendors. So we try and work very closely with the cloud vendors, and we say to them, how do you want to present your cloud stack so that you stand out and researchers can sort of understand and adopt what's going to really work for them. So that's a great relationship building process that we have built into the program. We do office hours. And we have a video series called Cloud 101, which introduces the basics. So that's to help the absolute beginner get started in understanding this computing paradigm. And then, as I mentioned, we're doing clinics also, which are monthly short sessions that delve into a particular topic to demonstrate feasibility of that topic's use. Lastly, this is my last slide. Before conclusions, we have, second to last slide. This is a recent project, Scott Henderson, working with a student whose name is escaping me, so I'll just slide on down here. Eric Gagliano. The point of the project is that this team of 2 people deployed a coiled compute cluster plus a storage container on Azure, that's a cloud, the Azure Cloud West Europe region, because that's where the data is. And so by deploying their infrastructure there, which is a compute cluster that's sort of like Kubernetes and Docker without that machinery, they were able to access 100 terabytes of Sentinel-1 radiometrically terrain-corrected data and output a global data set of runoff timing of snowmelt. And that's 1 terabyte output at a cost of less than $1,000, which corresponds nicely to the Access exploration tier for using Cloud Bank, if one were to try and do that. So Eric, of course, published his results, his software as open software, and this will turn into some publications. And Scott pointed out that if, in as much as NASA is going to be placing NISAR RTC and AWS US West 2, it'd be nice to do a parallel sort of community enablement step that maybe involve Cloud Bank Explorer grants to be able to do the similar kind of thing as NISAR data comes into play. So that's a quick high-speed tour of CloudBank 2. These clouds are available, as I noted. And also, I don't have time, but fortunately, Chad Truant will talk about Maureen Donnell's work in a seismology project, which also emphasizes a research team that's able to pivot to learning how to use and really make good use of cloud technology. So thank you very much for the opportunity to share this with you.
Very exciting. Thank you, Rob. And there was one question in the chat. If you have a question, we do have a few minutes. So please use the raise hand feature. Tim asked, do users get full admin access to cloud environments, or are there guardrails, limits, requirements imposed? And Joe has a response, but go ahead.
Yeah, I think the short answer is you're basically at admin level. And one of the nice things about the program being run by academics, specifically the people at UC San Diego who do all the operations, is that we are ready to work with you. If you run into problems, either accessing because of a quota limit or you don't have enough permission, CloudBank team is really happy to work with you. Very responsive on the ticketing system.
Great. All right. If there are no other questions for Rob, I'm going to hand it off to Chad.
Can you see my slides?
Yep.
Great. Thank you. So I'm eventually going to talk about a global scale database of seismic phases. But first, I'm going to give you a little bit of context. My name is Chad Trabant. I work for Earthscope Data Services. Earthscope is the merger of IRIS and UNAVCO, and we no longer say those names. So even though we only existed for the last 3 or 2 point little bit years, we have very, very deep roots in running the seismology and geodesy facilities operated by National Science Foundation. These all now fall under the umbrella of NSF's National Geophysical Facility, which we operate. So that's my context. In 2019, we did a big experiment with our seismic repository where we had a pair of researchers that were using AWS to consume data and then process it in a streaming fashion from our on-premise facility. So what you're seeing in the graph there, they used a 50-node cluster accessing a little over 5.5 terabytes of data. What you're seeing in the graph is the 80 hours of time that they spent accessing that data with our background traffic. So the background traffic is in gray. We're averaging there somewhere between 60 and 100 requests for data per second, which we thought was pretty skookum. This is really nice, like performance for an on-premise facility. We had probably built that facility over the last 30 years, and here came a single user able to nearly double that traffic. So this was simultaneously very successful. It took a real collaboration between the facility and the users that were driving this traffic to make sure it didn't make the entire facility fall over. But it was also quite eye-opening in the sense of this is a pattern of use access, which seems obvious in retrospect, that the on-premise facility simply can't serve very well. We are a limiter to this big data sort of work. So massively successful, but those numbers by today's terms are relatively small, 5.5 terabytes of data. And yeah, moving at 1.7 gigabytes per minute, not bad, but today's numbers are much, much bigger. So following the merger of the two organizations into Earthscope, now operating NGF, we have been working for the last many years on migrating our on-premise facilities into the cloud. Most of them are now moved. We have a little facility doing synthetic aperture radar data in Indiana. It's in a relatively stable spot. Our last on-premise data center is in Seattle. We're affiliated with the University of Washington, so it's in the university's machine room. And sometime in 2026, we will have all of that in the cloud. There's a significant portion of the workload already transitioned, but there are some last critical bits that need to move. And to give us some credit, I know it says we've been transitioning since 2019, but a few things happened in there. We had a merger of nonprofits, which was truly a corporate merger and required a reculturalization of our group. There was, of course, a pandemic somewhere in the middle. We recompeted for our 5-year award. We won that award. So now hopefully we're off and running with getting work done again. So that's the context. We knew we were having trouble serving a certain use case. We're now moving to the cloud. And what we really want to do is provide data adjacent compute. Finally getting to this stage, it seems obvious, but we're building a big system with an initiative called OnRamp to try to help our users transition from very traditional workloads, either on a small computer system at their university or within their lab or their laptops for the most part, into working in the cloud. This is a major transition. We're spending a lot of effort trying to help people make that jump. And of course, what we've done is build something like a Jupyter Hub system. We're partnered with 2i2c to build out something we call GeoLab. It is more or less a traditional Jupyter Hub, but then we will use this as a primary stepping stone for researchers to move off their laptop into the actual cloud compute and not move data around so much. This has a little bit of limited functionality. It's, of course, a notebook environment, so you can run all sorts of things notebooky. What it doesn't address is the large, I would call maybe a little bit older user base in our research user base that are Fortran users on their laptops. That's a little bit harder to transition to the cloud. It's still possible. This is also just a first stepping stone. We don't expect people to move into this environment and then process a petabyte of data. We do expect people to prototype that kind of work in this environment. So moving on to the big winner exercise that we did recently, mining the entire repository of seismic data. This group at the University of Washington, led by Maureen Donnell that Rob just spoke about, did this work over the last couple of years. I want to highlight 2 people in this work. Yi-Yu Ni is the primary architect of what the actual research group built and then executed that. And Alex Hamilton is the architect at Earthscope that did most of the facility work in terms of enabling that. And I'm going to describe what all that means, but these 2 are superstars in this piece of work. So this is what it looked like from the researcher perspective in the architecture that they built. So cloud native workflow to detect earthquake arrivals at stations. And this is using data across a couple decades which is kind of unheard of in the seismology world. It would take a long time to execute this not in the cloud. So they ended up with some sort of orchestration system on EC2s, just giving them access. They want to store everything and orchestrate jobs using a document DB cluster. SeisBench is a framework for running what's called PhaseNet, which is a machine learning-based, deep learning-based phase picker. Phases, for those not in seismology, are earthquake energy arrivals on seismograms. Of course, what we want them to read from is S3, and this is critical. That we don't want to provide a service that's in the way. We want them to use the full power of AWS's service. There was metadata that was still outside of AWS, that's still on-prem in Seattle, but honestly, that's a small part of the work and was not a barrier to the work. That will eventually also go into the cloud sometime this year. So what does this mean from the facility perspective? Restating that again, the goal is to allow direct access of AWS services and make sure that we do not put services in the way. Anything we would put in the way of S3 is just going to degrade the service. So the major challenges there are that AWS services require AWS credentials. So having an Earthscope account doesn't necessarily mean you can just touch the bucket objects directly. So we have to bridge that gap somehow. We have the further challenge that our restricted data is mixed in with the open data. So there's not a lot of clarity from just the storage layer of what is open and what is restricted. So somehow we have to gatekeep that. So the solution to that was this, where an actor comes in and goes through one of our public APIs, and then we use their Earthscope credentials to internally broker AWS credentials that they can use directly then with S3. That, of course, goes and looks at permissions in our fine-grained authorization service. And then that actor now has AWS credentials that they can talk directly to AWS services. We then used a restricted data access point, which then we run an S3 object Lambda on. This is one of the critical challenges of this work, is that this is now a piece of code of ours that's in the way of S3. We always have to go through this check because we have to know that they're not trying to access, we can't give them access to restricted data that they're not allowed to. And it's not very obvious which data are restricted versus not. So we're doing this check every single object access. And we have 40 to 50 million objects that they're moving through. So this is not a trivial make a list thing. And the permissions change from time to time. So this is the best we could do to try to get out of the way of them getting directly to S3. It is not ideal. We have a dashed line here that will make it much more ideal in the future. I'll discuss that in the conclusions. So the actual work was over, if you look at that timeline at the bottom, it's, let me go back. That's 72 hours of work time for the EarthScope portion of it. They also did some work on some open data sets and from the Northern California Earthquake Data Center and the Southern California Earthquake Data Center. That's what you see on the right. But what you see on the left is the number of jobs, which if you are paying attention to that graph, that's 120,000 jobs executed through AWS batch service, and how many were running actively at the same time and how many were pending. An important point to note here, this is a lot. That's 1,500 active jobs concurrent, and this was only limited by AWS credentials. AWS quotas. You can see at the very beginning, the default quota limit for AWS batch was 1,000, and they asked for an increase to 1,500. You could easily ask for an increase to more, and we got no real indication. There was no real obvious limit of why we couldn't have done more. It was just that this was sufficient in this particular case. So fantastically scalable. This is an absolutely clear use case that we could not support on-prem, and very difficult to do for someone if we did not have the data already in the cloud. So the workflow results, they consumed 1.3 petabytes of data in 72 hours. That's a huge boost from what I showed you in that 2019 study. Includes a 16-hour pause, like literally this gray area in the graph here, the timeline is a little bit of data checking to make sure that things were going right, but the grad student also needed to sleep. So this could have been done faster if only they, pushed him harder. Another detail was that it was limited by the batch quota system. I can't emphasize this enough that you can literally ask for more, and it's hard to find the limits in some cases of really fundamental AWS services like S3. The sustained request rate was 300 requests per second. It's peaking to 400. That's just super impressive. PhaseNet results, so how many picks they got out of this. From the EarthScope data set, they got 2.8 billion picks, and you see the Northern and Southern California sets there, but the total was 4.3 billion picks, roughly estimated into 50 million earthquakes. I know a lot of you are probably not seismologists. This is an astounding data set to work from. So this is fundamental and will become something that is mined for the next decade. And there will probably be 10 other groups that build competing catalogs like this, but this is truly game changer stuff in seismology. Of course, it's impossible to avoid talking about costs a little bit. It's certainly not free. What the research group paid was about $15,000 for workflow compute, so that was mostly the AWS batch service. The database storage is about $200 a day. The facility, because of that Lambda function that we had in between S3 and the user, we paid about $5,000 for this work. That's not ideal. You can't avoid costs, but we think we can mitigate some of those costs. So conclusions, we successfully provided data direct access to S3 objects, not in the most ideal way, but it was possible, and it allowed things to scale incredibly. This is game-changing potential for analysis in all of the data sets that we're offering from our facility. It still costs money. So of course, you can't avoid money. I think CloudBank plays a pivotal role in helping people in a couple of ways. One is trying to cost optimize, like what their research goal is, how to do financial operations. Researchers aren't used to the word FinOps. They did FinOps, of course, when they're rebuying computers and stuff, but the reality is this is a different kind of FinOps. They need help. CloudBank will be excellent at that, we hope. They also have a fairly large fear, at least our user base does, of what does it mean in terms of lack of skills to move to the cloud. CloudBank should be able to help them with that as well. In addition to us, we will be helping with that, but there's only so much bandwidth to help people. There is a lot of reskilling to do. You have to learn how to use the cloud. It's not impossible. It's possible even for people about to retire, but they need some hand-holding in the beginning. There's a fair amount of fear. So future directions for us, tagging-based access will allow us to avoid the expensive restricted data check, and we are going to utilize the AWS Open Data Sponsorship Program. We already have approval. We already have a bucket. We need to do some fair amount of work internally to try to figure out how to move data over there, not move, but copy data over there. That will further democratize access to all these data. And I'll leave it at that.
Yeah, Joe, go ahead with your question real quick.
Yeah, I'm curious why you mixed public and restricted data in the same object store and didn't split those into two buckets.
Sure.
Because then, especially with the sponsorship program, like you could then just provide a public bucket with nothing in the way for your public data.
Yeah, so the answer is easy. We wouldn't have done that if we were building from scratch. We're building from a 40-year history, and we are still mirroring the data from our on-premise data center into the cloud. So we cannot restructure, reorganize the data right now until we are off on-prem, because we simply don't have the resources to shuffle the data in two different places. And there's no downtime. We're still handling, at this point, we're handling about 200 requests a second. So we're not reshuffling the data just to get rid of the restriction mix with open data. We might get to that point, but we'll only be able to get to that point when we're not synchronizing data across multiple data centers. It's definitely becoming an increasing roadblock.
Yeah. Okay, we should continue on. Thank you so much, Chad. I'm going to pass it off to, well, before I do that, I just mentioned Tim also has a question in the chat. So if you don't mind looking there, Chad, and trying to respond to that, that would be great. Yeah, next up is Eliana.
Hello. It says that I need to request sharing. Oh, I can share now. Perfect.
Just give it to him.
Thank you so much.
And we can see your screen, so it looks good.
Awesome. Thank you. Thank you so much for having me here. This has been such a great session, both this morning and now. And I also really enjoyed yesterday's session on chunking. So it's exciting to be here. I'm Eliana Abrams, and I work as a research software engineer / data scientist at the Center for Computation in the Stanford Doerr School. And so I sit a little bit further down the pipeline than I think a lot of the talks have been here today, where I kind of am positioned between the people thinking about how we store data and keep our hardware systems running, whether or not that's in the cloud or on cluster, and the researchers who are kind of trying to use these systems as seamlessly as possible in order to get their research done. And so today I'm going to talk to you about a tiling strategy to access Earth observation data in the cloud that thinks about the way that we chunk these data and what are the downstream implications for that kind of chunking when trying to run machine learning on Earth observation data. And so to start, let's put this in context with where these kinds of analyses occur on the cloud. And so while we do have data stored in buckets or other object storage, the analyses themselves occur in compute. And so this will be in some combination of CPU and GPU compute. And this is because typically GPUs are very powerful and can run complex computations rather quickly, but they do have a strong limitation, and that is how much onboard memory they can carry. And so here I've listed 3 very popular cloud compute GPUs. These are all available on AWS and GCP. That's the NVIDIA T4, the V100, and the A100. Chad mentioned earlier about the cost of these things, and deep learning and foundation models are very popular right now, but it's important to keep in mind that every second your analysis is on a GPU, it is really running up costs. So the cheapest one here, a T4, costs about 50 cents an hour. But an A100 can cost up to $6 an hour. And so when trying to run compute on really large data sets, we want to optimize as much as possible how we're loading and unloading that data in order to get kind of the best downstream results the fastest possible. And let's think about this now in the context of scientific imagery, which is much larger than that onboard size that we see on the GPU. And so here is an image from Landsat 9 of the San Francisco Bay Area, where I am right now. I've highlighted the Golden Gate Bridge with that little yellow star so we can orient ourselves in the image. And Landsat takes these images in 5,000 by 5,000 pixel scenes with 10 color bands every 16 days. The Eta 9 constellation has done this for over 12 years. And in just 1 year, in just this one location that I'm showing here, a single Landsat image cube, which that image kind of passes over every 16 days, is greater than 46 gigabytes. So that's greater than most of our cloud GPUs. But let's say we want to look at multiple years. If we're looking across 2 years, we've exceeded the onboard memory size from the largest GPUs available in the cloud. And so for this reason, it's not only necessary to chunk our data from a storage perspective, in which we don't expect people to interact with, from the talk earlier, all 35 petabytes of a single year of NISAR at one time, but we also need to chunk them from a hardware perspective. Our compute just cannot handle these large images all at once. But what kind of implications does that have if we chunk an image? So here as an example, I took that image and just divided it into 4. But this changes the underlying distribution of these images. Before, we had notions of continuity across these tiles, and now all of our algorithms see them as distinct from each other and non-continuous. And so again, I'll just highlight the Golden Gate Bridge because we're going to show kind of the implications of this as we go through the talk, highlighting the Golden Gate Bridge. Before, it was connected to the rest of the Bay Area, and now it is only connected to a part of it. And what kinds of effects does this have ultimately on the science we want to achieve? Let's say, for example, image classification. And so I'm turning now to a scientific use case. When I was a scientist, I typically studied polar data in the Arctic or the Antarctic. And when people are running science, like trying to understand what land cover classes are available, they're typically interested in the rare events or things that occur less than other things. And so in this case, I'm showing Ellesmere Island at the northern boundary in Canada in the Canadian Arctic. It's easy to see where there's barren rock, where there's snow and ice cover, where there's water, but maybe it's harder to easily distinguish less represented classes like moss and lichen or grassland. So one of the reasons it's harder to see that is those particular classes that I just named are much more underrepresented than the other classes. They only make up each less than 5% of the pixels in the image. So who labeled this image and how did they do that? Well, a team of scientists working for the Canadian government did, and they did so by going in by hand and specifically looking for the more represented classes in the configurations that would lead to the growth of grass or lead to the occurrence of moss and lichen. So they might look for where water is adjacent but not on top of rock, where there's a lot of snow and ice melt. And so we want to think about ways that these contexts that could get sliced off when we're chunking our larger overall images might change the downstream effects when trying to automate classification across the entire Earth. And we also want to think about how we can automatically chunk in order not to erase these contexts. And the reason automatic is important is that if we could create chunking that was initially mindful of where these underrepresented classes were, that means we already know where they are, and then we can just skip the whole very expensive in the cloud process of deep learning and not use GPUs at all. And so let's think about ways to automate this. And our team was not the first people to think about this. If anyone here has heard of an algorithm that's rather famous in the computer vision world known as the U-Net, in that same paper in 2015, they thought, well, if we just run kind of this tiling that splits all of our medical images into pieces, we lose important context, and this affects our deep learning outcomes. And so they created what has been considered for a long time the state of the art in preserving these domain contexts, in which they create overlap. So rather than creating 4 tiles on the previous image, let's walk through what they do when they overlap. So we're starting with that same image of the San Francisco Bay Area with that same initial tile that we had before. But rather than moving the tiling window or chunking window over entirely, Runneberger et al. 2015 proposes just sliding it by 50%. We've got an overlap, slide it over now again by 50%. So we've got all those overlaps, slide it downwards by 50%, slide it diagonally by 50% in XY. And then we have a bunch of overlaps. So we've got these multiple contextual views. This is great because it extends our data set, preserves contextual views. But there's one challenge here when we think about this. And we're going to highlight that Golden Gate Bridge again to look at that. We'll see that the Golden Gate Bridge was only represented one time before. Now it is represented 4 times. And each time it's represented, it's in that same orientation. And so we have actually not just extended our data set, but we have fundamentally altered the underlying distribution of the data set. And so now we're not looking at the same data. And so we propose a different method. Luckily for anyone who has run deep learning, typically in computer vision, somewhere there's something called a convolutional layer. This relies on the mathematical algorithm of convolution, which has this unique property that if you put in the same matrix into convolution, because it's very geometrically bound, if you mathematically permute that matrix, it is now seen as distinct at the convolution stage, and it serves to extend your data set without creating any redundancies. And so we realized that we could use the same overlap method, but as long as we created unique mathematical permutations of every time those pixels overlapped with each other, then we ended up with these chunks that we could load onto the GPU that were now distinct and removed any redundancies from the data set. And so that's what we did. Let's take a look again back at this picture of the Bay Area. Here I've highlighted the Golden Gate Bridge in a pentagon so we could see how creating those unique mathematical permutations change those underlying matrices. So again, we're going to slide over in 50%, but now we're rotating by 90 degrees, and you could see that the pentagon is in an entirely different orientation. And so this introduces 0 redundancies as long as we have a convolutional layer. The same happens when we slide down by 50%. Now, instead of rotating by 90, we rotate by 180. Slide diagonal in XY, now we rotate by 270. And we did the math out and found that there were 8 distinct mathematical permutations that we could do that still allowed all of our data to remain physically true to the kind of data that would be observed by a satellite. We didn't want to create color shifts or blurs because in the end, that just creates redundant learning at the GPU stage. And in the cloud, these GPUs are expensive. And so we really want to restrict our learning into the domain space in which every single pixel and every single second on the GPU counts. Ultimately, this actually had the outcome of just making this slight change in input, which is really where the inexpensive compute occurs. If we can make these changes at the pre-processing stage, like we've done here, and use a GPU in the cloud only for that meaningful learning, it really helps balance out our costs. And so when we do this figure that is here on the left of the screen, essentially what you see in this left column in the overrepresented data, that snow and ice, it really doesn't matter how you pre-process if you're looking for something overrepresented. But if instead you're interested in something that is underrepresented in your images, here lichen and moss makes up less than 5% of the overall pixels, the ground truth is shown in that first row. Our method, which we nickname flip and slide, if anyone like me grew up in the 90s remembers the slip and slide, it's just because we're flipping and sliding our data as we go along. And flip and slide, you could see that in lichen and moss, it does a much better job of approximating and estimating that true underlying distribution than it does with just that simple 50% overlap. We wanted to make this really easy to use in the cloud. We actually developed this on CryoCloud in a single T4. And so we've released this code on the Python package index. It's available with a quick start guide here at this QR code. If you're curious about the paper, it's available there on arXiv. And you can insert this really neatly into all of your pipelines. It's cloud optimized, and it will output data in PyTorch tensors, TensorFlow tensors, and NumPy arrays. And we're right now working to create better ZAR capability there as well. And that's my talk today. Thank you so much for listening.
That's great. It's great to see these ML downstream applications, because I think the use case of this data on the cloud is a lot more complex than sometimes us at the data systems level always think about. So it's really great to hear about that. Do we have any questions for Eliana? We have a few minutes. I was wondering about the choice. Oh, Madeline, go ahead.
I wanted to ask you a quick question. I'm happy to continue this conversation offline because it's a bit of a newbie question, but say you're a researcher, grad student, maybe like myself, and you have an idea that would make great use of what you just described, but you're totally new to everything in this session. What would you suggest be the first place to start? I can go through the docs and stuff, but I just, is there like a big kind of like onboarding, trying to understand like all the background to these technologies first and then go into something like this? Or do you feel like this is something that is fairly easy to use out of the box? I'm just curious.
That's a great question. And welcome to the Deep Learning on the Cloud. We're all new there and learning what's going on as we go. I did try to make the Quick Start Guide accessible for someone coming in new, but also this is very much under active development. So please feel free to reach out directly to me. If you have an issue, open an issue on the GitHub. We completely welcome any contributions as well. So if you find as you're using it and something changes for your particular use case and you want to push contributions to the package, like, please join us.
Awesome. Thank you so much.
Just a quick question, I hope. So is Flip Inside basically, it's not geospatial specific, right? Like, does it have applications to sort of all like deep vision learning?
Yeah, that's a great question. So at the moment, it's not geospatial specific. We do have integration with Planetary Computer. So people could either, let's say, use Earth Access, get the image they're interested in, and run Flip and Slide on it. But if they're very new and, let's say, haven't used Earth Access before, we also have the ability just to drop in coordinates of interest, and Flip and Slide will interact with Planetary Computer and automatically tile from there.
Oh, amazing. Very cool. Okay, great. If you have more questions for Eliana, feel free to drop them in the chat. And next up, we have Raphael.
Sweet. Thanks, Amy. Can you see my screen? Sorry.
Yep.
Great. I have some Zoom thing in the way, so I can't switch tabs. All right, here we are. Hi, everyone. My name is Raphael Hagen. Thanks for coming. So today I want to talk about using Coiled's collaborative software environments for some of the projects we do at Carbon Plan. We're a pretty small group, and Coiled is like a for-profit company that kind of makes this usability of the cloud much easier. It's really cool to hear about things like CloudBank, though. Didn't know about that, and I think that's a good option. So a little bit of background, I work at a small nonprofit called Carbon Plan. Our mission is to improve the transparency and scientific integrity of climate solutions by building open data and tools. We've done a lot of different areas of work. This project back in 2023 was some work through the ESIB lab, where we built a near real-time fire monitoring dashboard, and we used it to see how forest fires were impacting carbon offset projects. So specifically, these forest offset projects a lot of them were being burned, and you could see in real time how many acres were being burned up. We also do some work with journalists, a lot of it in the kind of climate impacts space. So this is some work we did with the Washington Post, looking at the future of extreme heat at cities across the world under different climate scenarios. So we made some nice maps of showing how extreme heat is going to change in different cities. We also worked with another small group called Seaworthy, who does direct ocean removal of carbon dioxide. And this is a little example of an interactive web tool we built with cloud computing to show how their models worked for direct ocean removal. Almost all of our work is done because of these great tools in the Pangeo ecosystem. Most of these tools and work is all cloud native, or it works really well in the cloud. The kind of probably two most common ones we work with, or you've heard about, are Xarray and Zar for manipulating data and storing data in a cloud-friendly way. About a year ago, we started a new project, which I think in about a few weeks, we should have a cool blog post and map on. But it presented a bunch of new challenges, and we used Coiled really extensively to aid our kind of cloud compute. And I just want to talk about then the challenges this presented and how we used Coiled to get over them. So in a lot of our previous projects, we're working with gridded climate data. A lot of this is at, maybe a 25-kilometer pixel. Maybe if it's downscaled, it's to 4 kilometers, but it's pretty low spatial resolution. And this upcoming project, we're using this much higher 30-meter spatial resolution raster input data. We also paired it with some vector data. So in this case, we used about the 175 million polygons that are over the continental US, so that we could merge this raster and vector data sets to get sampled building polygons, so scores of individual buildings. If you've done some of these like zonal stats and other GIS operations, this isn't something you could probably do on a laptop with QGIS or ArcMap. So we really needed to reach for some larger cloud resources. Also, we set out a few kind of like high-level goals of this project. The first one is we wanted to build this pipeline that would scale well with increasing complexity. So as our project scientists maybe increase the complexity of their models, we didn't want to have to rewrite the pipeline from scratch and say, why isn't it working? We tried a bigger compute, it doesn't work. We also wanted a click and run sort of pipeline. So in this way, you click a button on GitHub and you wait a few minutes, dispatches some work to Coiled and the cloud, and then you have your data showing up in a web map. This is really nice for quick iterations of changing little tweaks in the science pipeline. And all of our work we like to make open source and reproducible with version data outputs that are publicly accessible, thanks to Source Cooperative. So getting into title slide, we use this service called Coiled. So this is a small company that kind of acts as a bridge between a user and one of these major cloud providers like AWS, Google, Azure, so forth. These huge cloud providers are spending tons of money, make it quite hard to use the cloud, or they're getting better, but it's still pretty tricky. I think this is why like CloudBank and a lot of these other orgs exist to bridge this divide. Coiled provides a lot of resources and different tools. I'm going to talk about how we use those and how they kind of impacted our project. So first off, Coiled gives you this really nice thing where it says, whatever local Python environment you're using, whether that's UV or Conda or Pixie or something else, it'll just duplicate that, put it on a cloud VM, and run it. You pretty much don't have to think about it. And this is really nice if you've ever had to mess with building Docker images and deploying them on cloud, like Lambda functions. It's quite a pain. So this just kind of like does some magic for you, so you never have to worry about it. It also has the ability to run batch jobs. This is really cool if you're coming from maybe a cloud Jupyter environment where you run one, wait, run another, wait. This allows you to run multiple independent batch jobs at the same time. And they make the syntax really easy. So there's just a CLI, so you could run this pipeline job, and you can define config in a really simple way. So here, it's a little syntax of like saying, go grab me a VM of this size, put it in this region, maybe attach a disk to it, maybe use a spot instance, but all these really easy user configurable settings. They also give you this really nice dashboard to monitor your jobs in real time, whether that's like a Jupyter Notebook or a batch job. You can spend a lot of time just looking at these, seeing the CPU usage change of your job, memory usage, your throughput. I found this a really nice tool for tuning jobs. So you can be like, oh, wow, I need maybe a more compute intensive environment, or I can save some money and use something with less RAM. So it's been really nice to control costs. They also provide a way to use notebooks in the cloud, just like a hosted Jupyter Hub, but you do it with a single line. So you say Coiled, notebook, start, go grab me a VM of certain type, and then you can also sync all the changes to your local environment. So if you're working in some IDE or VS Code or whatever you want, you can be working what it feels like locally, but you actually have the power of a cloud VM. So kind of complex pipeline diagram, won't get too much into it, but I just wanted to say, like, how do we use all these pieces in this pipeline and how do they help us? So first of all, on the broad scope package sync, we all, at multiple people working on this project, we all want to be on the same page. So we have a package manager like Pixie, so we're all in the same compute environment. But the nice thing was the Coiled package sync would just duplicate that environment, and anything we run, we know we're running on the exact same environment. So we don't have this worked on my machine, this worked on your machine, this worked on the cloud machine. It just kind of works. I mentioned earlier that we had this sort of project goal of a scientific pipeline that scales with the increasing complexity. So some of the project scientists were tuning models and making things harder for us. We wanted it so we didn't have to just rebuild everything from scratch. And if you've used kind of the Dask Xarray distributed computation ecosystem, you might have run into problems with this before. A lot of times you'll get this Dask task graph that looks really nice, bars are flying by, and all of a sudden something doesn't work, you run out of memory, you're not really sure what's going on. And this just leads to a lot of headaches. So we wanted to kind of avoid this, and how do we wouldn't have this in the future? So we took this approach that a few people have documented in the kind of Zar Xarray world, where if you have a job that can be split up in independent regions, you can create a template or a skeleton of what your data is going to look like in the end. So here I have a picture of the continental US split into different spatial regions. You write this kind of skeleton or template with no data, just the shape of it and the metadata attached to it. And then if your computation can be split up, you can use something like coiled batch to say, hey, I have a few hundred independent regions. I could get a few hundred independent VMs with coiled, and I'll run those all parallel on the cloud, and they write to the region that was specified. We added another little flurry on top of this new open source tool called IceChunk, which gives you kind of like a Git-like transaction for your Zar data. This proved really useful in kind of this retry scenario. So if you run maybe 500 or 1,000 different regions, and for some reason one or two of them fail, you can rerun it and it'll just only rewrite the regions that were missing, kind of avoiding a lot of just extra compute and just headaches. Coiled real-time monitoring, it's not only useful for like small jobs like notebooks, but really cool for running these batch jobs. Here I have a plot. You can see over time, the VMs or the batch jobs scaling up and down as they get work, do the work, and then shut down. This is really nice. So you're not having something just running, even though it's already done, which happens a lot in like JupyterLab environments. So once we had this big pipeline working, we get this 30-meter process data product. This is me just kind of zooming in of a raster multi-scale pyramid. I live in Missoula, Montana, so I'm zooming there. So as you can see, we're going from continental US all the way down in the Zar like multi-scale pyramid down to a building level. Part of this pipeline was this Xarray raster land, but we also added this kind of GIS-y vector land. So we wanted to sample out building polygons to this data product we created. So if you want to do some of these GIS operations, a lot of them are on like not distributed systems, like a single machine. And doing these big operations on a laptop would really work. So we use coiled batch again to say, go grab me a VM with hundreds of cores, tons of memory, and do this big GIS problem, and then write to the cloud when you're done. We use DuckDB Spatial for our GIS operations, which is just great in the cloud. And then another C++ program called Tippecanoe, which builds these multi-scale vector pyramids, kind of like I just showed you the multi-scale raster pyramids. The really cool thing with coiled batch is it doesn't have to be a Python batch. You can say, hey, I'm running this weird shell script or C++ or maybe some weird Fortran climate model. I just say, hey, go run this. It grabs a VM and does the work for you. So once we had Tippecanoe and DuckDB working, we also created this multi-scale pyramid. Instead of the raster gridded product, this time it's actually just the buildings. So there's individual house level, shed level buildings. And this is all in the cloud too. There's no server giving this. The last kind of bit of the coiled tools we're using was Jupyter Notebooks. This isn't new. Like you can, of course, use this with some managed service. But coiled just makes it easy. It's one line. And you start a notebook right where your data lives. So our data is in, US West 2 of AWS. We grab a VM in the same spot. And this is really nice because you're not getting any egress costs by pulling data out. And it's really high performant because it's sitting right next to where the data lives. This is really useful in our pipeline for the project scientists to be able to do like QA and QC checks. So at different points, they want to look at something or they say, hey, I made a change. What does it look like? They could quickly spin up a notebook and pull data in and do visualizations and plots. So takeaways. This was really helpful in this project, all these coiled tools. I think they just make it easier to work with a lot of these cloud providers. I will say kind of a downside is like it is, a single private company and it costs extra. So I think like for a lot of people, this is difficult. Like if you're a grad student or a small lab, it might be hard to justify an expense on top of paying for a cloud bill already. So it's really cool to hear projects like, forgetting the first presentation, to just provide these resources, which is really neat. I still think there's kind of a gap of Coiled one option, but it'd be nice if cloud resources were much easier to use. I think Coiled just shows you that you can do this really well. Just want to give thanks to all the Penju community for building all these open source tools that we use every day and rely on, and then all the ESIP partners and session organizers. Amy, if you have any questions or want to just chat, my email is Raphael with a PH at carbonplan.org. Thanks again.
Awesome. Thanks, Raphael. And we do have a question from Luis I'll read out. And if somebody else has a question, please raise your hand. So Luis says, we did something similar for It's Live, batching based on geotiles, but we ran into imbalances with regions with high density versus low density. At the end, we had to partition the data evenly, which meant no same area tiles-based distribution. Have you run into this?
I think if I'm understanding with like the kind of the vector pyramids with Tippecanoe, that was like a similar thing where, there's like, in New York City, there's a bunch of buildings, and then in Nebraska, there's nothing. So I think we had to spend a lot of time tuning like the sort of like there's 10,000 different knobs in Tippecanoe of like when you drop tiles and when you kind of set your size limit. Not sure if I'm really quite guessing your question, but yeah, I feel like with this non-uniform data, it was really a pain.
Yeah, I think it's basically that, like you said, like you have, say, New York, high density, buildings, and Nebraska, there's nothing. So if you send like that tile to a node, it will finish in, say, 10 seconds. So it's a lot of overhead just to basically, do not a lot of processing. Totally. And because we were using on-demand, not on-demand instances, but like the ones that are like half price, but you're bidding for the spot instances. Then sometimes we had like, these imbalances in processing where like, okay, this is not working.
Totally.
And I don't know if you guys run into something like that with that.
Yeah, we were using like spot instances for that like kind of distributed like coiled batch job for like the ice chunk bit or like the Czar ice chunk stuff. And that was nice because like if a spot instance would get taken back, we could, on the second run, like the second attempt, check through the version history and say, oh, that's missing. But for the like vector pyramids, it was all like on a single VM in Tippecanoe that wasn't spot. So we didn't have any like pullback bits there. But I think there is some definitely inefficiencies of like what you said of like, hey, some VM needs to do a tiny little bit of work, and with that much data, is it worth spinning up? I don't know, but yeah.
Yeah, makes sense. Okay, great. Thanks so much, Raphael. And I'm going to hand it off to our last speaker, Puneet.
Everybody, just give me 1 second. I'm going to share my slides here. Okay. Can I share a tab? That's what I want. There we go. All right, can you all see?
Yep.
Fantastic. I'm all the way back there. Sorry about that. All right, everybody. Well, thank you so much, Amy, and thanks to all the speakers who came before me. And I'm really grateful to have the opportunity to close out this session with a talk that I'm hoping will wrap up a lot of themes from the other presenters and bring in some broader social, cultural, policy, and economic context, kind of looking at a case study where I've been using a variety of different approaches with my collaborators, including the cloud, in order to preserve data that was recently taken down, data that has proved to be far more useful than a lot of people might have originally envisioned, and the cloud kind of serving as one ingredient. But there are lessons from that I'm going to discuss here. I guess the first thing I want to do, though, is kind of tell you a bit about what I mean by data preservation, but also how I got here, because there is kind of a long journey here. And I also think that data preservation is just a first step. What we really need to talk about to some degree is how to foster data resilience, because preservation is really just one step on a far longer road. And you can do all the work in the world to preserve a given data set or a data repository or collection or tool. But once that data collection or tool, goes offline in an emergency or something, then what do you do? So, I have a kind of a multidisciplinary and cross-functional background, having started as a science and environmental journalist, spent nearly a decade doing that before becoming a data scientist, and fairly recently focusing on geospatial, environmental, earth and climate data science and analysis. And a number of events along the way really, I think, proved formative to me in helping me kind of get onto the broader data preservation and data resilience movement. I think first off, just having covered a lot of federal programs and their data ecosystems, it really helped me appreciate just the public goods aspect of so much publicly funded and supported data, just the benefits it brings to people, even if they aren't actively consuming them. And also just kind of the pandemic, how it shaped the way I look at the interconnectedness of things, and how it really helped me appreciate that we can have a lot of science, a lot of data, great software, but oftentimes it's not going to be enough to solve the problems. You got to get people using them. You got to make them useful. You got to understand where people are coming from. And I think my journalism experience really helped bring a lot of that together, and to help me kind of bring people together around the broader ideals of what open data means and kind of the value that it provides. So early in 2025, that's when a lot of environmental, climate, earth, and other kinds of data sets were starting to be taken down, along with web tools and maps that you could use to kind of interact and understand that data in a better way. I sort of just took one step after another, but kind of a happenstance occurrence where I ended up being able to moderate a guest session on data preservation as part of this career accelerator program I did called Climate Base. And that in turn kind of put me on the path to joining the Public Environmental Data Partners, which is this kind of loose coalition of groups that works to preserve and promote public access to environmental data sets, tools, information, and so on. Now, early on in 2025, you might have seen a lot of headlines like these throughout the news, and many of them are describing, I think, some of the data sets that you all might be familiar with, environmental justice data sets and other kinds of government statistics. Source Cooperative, for that one on the bottom right, the data.gov archive, Jed Sunwall and Source Cooperative, they ended up partnering with the Harvard Law Library Innovation Lab team to create this archive of all of data.gov, and just, I don't even remember how many terabytes it is. I think it was like 16 terabytes or something and growing. And so you might have seen a lot of stuff like that. And it was often couched in terms like data rescue and, saving the data. And, we're going to grab all the data and just, we're going to be the heroes as a result. That's kind of the framing that I think ended up being common in the media, even if that wasn't the intent or like the original motivation for people to do these things. But I think that really underscores a broader point I want to make, that archiving data is just a first step. Just because you save it doesn't mean it's going to be valuable or useful. You can download the data to your hard drive or put it into a Google Drive folder or something like that. But how do you ensure that people are actually using it? How do people understand what its strengths and limitations are? Is it in the right format? Does it use the right standards? Can people use it in their preferred tools and languages? And you really need to, I think, take proactive efforts in order to actually get to that point where people can make use of that data. And I think there's a broader question here, though, about data resilience that I'm going to get more into. And that is, you can put the data up there and you can do all these great things, but then how do you ensure that it stays there and that it's sustainable in the long run, especially in cases of funding disruptions or emergencies? Those are really, really difficult questions to answer. And it takes a lot of careful, deliberate coalition building and discussions and planning. And I sort of like how Eric Nost, who in fact was the guest speaker whose session I got to guest moderate, last spring, I really like the framing that he used. He wants us to look beyond the data heroes framing that was common in the media. And he kind of asks us to embrace this broader picture that looks forward over time, from the present day to the next decade, from responding in the here and now to strategizing toward the future. from rescuing data to forming these broader collectives and collaboratives to, steward and then govern data. Thinking less, not just about data sets and tools, but also how are people using that data? And then not just the producers and the creators of that data, but who benefits from them? Who are those people in frontline communities, who are ultimately benefiting because data was used to support, investments in adaptation measures and things like that. In terms of what ESIP is doing along those lines from a resilience standpoint, just one example right here is the Repository Resilience Initiative. I was very fortunate to have attended that session yesterday as part of the January meeting. And this is a discussion that's been going on, of course, for many, many months now. But I encourage you all to check out the scorecard that they've got and try it out if you work with a repository or data collection and you kind of want to see, okay, how many fail safes are there, redundancies, funding streams, and procedures. Now, the example I want to focus the rest of the time on is this example of a data collection that was commonly used in disaster and emergency response. It was called High Field Open, kind of a long acronym there, but I think it really provides a useful case study. After 9/11, there was this broad reckoning among the emergency response management and resilience communities that nobody really had the same picture of where people, buildings, and important assets were and how vulnerable those things were. And it arose from this problem called the M drive problem. Maps and data sets were just scattered all over the place. Agencies, jurisdictions, levels of government, IT systems were fragmented and not standardized. File formats, shape files, Excel. You had people sending versions of data via email. And I really like, the example given by Adam Simmons from Project Geospatial in that pull quote below. A power plant on one agency's map was a mile away from its location on another's. When you have lives on the line, those kinds of issues really, really matter. And I think that's sort of a useful example of what sort of guided folks to work toward addressing this. And so data just serving as one bigger ingredient in getting toward a shared picture to support resilience. And so first off, you need to have the right data on the communities, the assets, and their locations and what their vulnerabilities are. But then you actually need to do the hard work of bringing them together. You need to find that data, curate it and standardize it, put it, into the right database and provide the right tools and interfaces for people to use it, and then maintain it over time and govern it and steward it. And so there was this coalition of the willing effort that emerged in the government to bring all this data together. The original vision was to kind of create a common picture, but then it evolved because they realized it wasn't just going to be one map. It was going to be hundreds of data sets and layers that formed a broader portal or collection. And at the time, this was, relatively speaking, novel, and especially in the government context. The common thread here was, what are the dangers to critical infrastructure in the communities around them? And that being things like buildings and hospitals and power plants, substations, nursing homes, and the like. And so the resulting product that came together over a really long time was known as the Homeland Infrastructure Foundation Level Data Program. And it contained two parts, a secure, sensitive version, and then this open version where you could, anybody in the public could go browse this and look up data and view it through this Esri-based interface. Just one example right here on the screen. The use cases for this were pretty far reaching. In terms of the broader anatomy, though, one of the things that I think is really important to keep in mind here, it wasn't just about data. It was about what it did with that data, where it put that data, and how it centralized it, provided it in a standardized format. And that really, I think, helped reduce the frictions to getting it into the right hands, for emergency responders, first responders, resilience officials, and the like. And so that, I think, was really the key here, not the data itself, but where it was and how it was packaged together. And so the use cases here, there are so many that I could go on forever about this, but you got everything from disaster response, how do you stage resources, how do you evacuate people, getting first responders to the right places, all the way to how do you upgrade buildings and build adaptation measures to protect communities from floods. Or, for those of you who enjoy football or Taylor Swift, this was used for helping protect events like those, including, Taylor Swift concerts and Super Bowls. So many different domains and the use cases associated with them, from energy all the way to public health and education. Unfortunately, DHS announced that it was no longer a priority to maintain this resource, and in August it was shut down. Now only the secure version remains, and while most of the original data sets are still available, now you have to do the legwork of tracking them down and then setting up new pipelines to get them standardized and merged into whatever workflow you're working on. So you have more hoops to jump through, and that really, I think, destroyed a lot of the original value associated with HIFLD. In emergency responders and disaster responders and such, now we're going to have to do more legwork, and that's going to slow down how you respond to emergencies or decisions on where you invest in adaptation and resilience. Of course, in came the data nerds. Certainly one of the things that had to happen was the data, getting snapshots of that data, and there are multiple efforts, some of which are grassroots, some of which have more institutional involvement. The Data Rescue Project, they've got a near complete snapshot on the Data Lumos repository, and then Seer AI, in conjunction with Source Cooperative, they have a HIFLD snapshot. Most of the data sets from there available both on the Seer AI website and on the Source Cooperative collection. So, and even Reddit has kind of gotten in on the action. There was somebody who grabbed all the data sets and put them into Google Drive as compressed GeoJSONs. Now that there's some pretty clear limitations that highlights, how many folks are going to be able to download all that data, uncompress it, and then figure out how to work with it. And that really, I think, strengthens the case for a more cloud-driven approach to all this. And just to kind of reiterate here, the data archives, they're great and all, and it's an important first step, but that's exactly what it is, a first step. And you have all these considerations from before that we have to consider again. How do you make the data useful and discoverable and interoperable? How do you ensure it's resilient? And how do you ensure that there's redundancy and diversity of funding streams and community-driven governance to ensure that one person's decision or one agency's decision doesn't lead to its discontinuation again? And that's where the effort that I've recently started working on comes into play. We've called it HIFLD Next, at least for now. And again, much of how I got involved was just chance encounters, starting with HIFLD Open being discontinued and then progressing from there. One talk led to another, one conversation led to another, working with some of the folks whom I quoted earlier, the insights that they had provided. And eventually it resulted in this funded effort through the Open Environmental Data Project in conjunction with the Public Environmental Data Partners. Again, both are partisan nonprofit organizations that kind of work toward building open environmental data ecosystems and promoting public access to open environmental data. Now, we identified two kind of competing imperatives, but they really weren't. First off, there was obviously a need to get the data back online as quickly as possible. We found out from some folks that there were use cases that we hadn't even anticipated. Some folks were working well beyond the disaster emergency space, and then there were data sets like judicial boundaries that people couldn't find anywhere else. So this was a case where, okay, there's a real need to try and restore relatively quickly. But in terms of how you promote the data use and then, promote data resilience, that's a much more difficult question. And it takes time. It's not going to happen overnight. You got to make a lot of decisions, talk to a lot of people, interview a lot of stakeholders, and so on and so forth. And it also costs money. You got to set up the tools. So the question was, what did we want to do? Did we want to work fast or slow? And the answer was yes. We did both. And two folks in particular kind of helped guide us there. The first off being Project Geospatial's Adam Simmons, who's got this blueprint, if you will, for how to build an open source successor to HIFLD Open, with a community-driven governance and stewardship model, as well as, just trying to consider how do you standardize and curate the data, a variety of technical and social considerations. That's a longer term consideration. But then in the near term, that doesn't mean you can't do anything. One person, Bill Dollins, one of the original contractors who worked on HIFLD, he told us, you know what, you can talk all you want about these fancy tools and interfaces and Stack and AI and this and that, but his advice, just ship it. Just ship something, get started, and have something out there that people can comment on, critique, and tear apart. Even if it doesn't look pretty, at least you can get the ball rolling. And so that sort of getting it out there and making it open kind of begets this virtuous cycle of openness. I'm not going to spend too much time on the tech build because it's still very early, but some of the things we've been using include GeoServer, GeoParquet, PM tiles, OGC feature APIs. We're trying to include some features right now that'll help give us a starting point toward a more resilient portal, including, dataset versioning and points of redundancy. We want to make, add some searching and filtering and subsetting features over time, and just try and make it more as interoperable as we can. But we got to get started somewhere. Will this be the answer? No, I don't think it will be. But it doesn't have to be. I'll just briefly walk you through like a very preliminary sort of concept for how it might work. You start off by browsing the collections, and you can search for a given kind of layer, the private schools one in this case. And then I'm not sure how well you can see this, but you can download a GeoParquet or PM tiles, or, you set up an integration through the OGC feature APIs. Again, this is just a starting point. The question is, now what? What do we do next? And this is where the next part of it all comes into play. We're really hoping to set up kind of this governance and stewardship framework that'll take us through 2026 and beyond. And this is where folks like you in the community are going to be really important. We want to do this in conjunction with folks who care about these issues, who are impacted by whether this data is available. Maybe they know people who are impacted by the data's availability. Maybe they've worked with the data before. We want to hear from you, engaging with users and stakeholders early and often. That way we can iterate and improve upon this over time and really make this something that is useful in the long term. I just wanted to, thank Amy Barciauskas for inviting me to give this talk, and so many other folks I wanted to thank, including Jed Suttonwall from Source Cooperative and Radiant Earth, ESIP, Federal, and then Adam and Bill, of course. Just so many folks that I'm grateful to. Really looking forward to hearing from folks about what we can do to get the ball moving forward on this, and providing as much value as we can in restoring and stewarding Highfield Open. So thank you so much.
All right, great talk to close us out. Thank you, Puneet. Does anybody have questions or comments on that presentation? I guess regarding the Highfield data set, could you repeat again, if I missed it, what's the current activities around maintaining it? How is it being maintained?
Yeah, sure. So if you mean in terms of the Highfield Open collection, it's no longer being supported by the federal government, by DHS. The data sets and layers, there have been snapshots that have been taken by various actors. Again, there's one that's hosted on Source Cooperative in conjunction with Seer AI. And then, of course, there's the Data Rescue Project. Those are two of the bigger ones that I've heard about. There are other efforts that I've heard about that are ongoing, but some of them haven't been publicly announced, and they're still kind of hypothetical. And the thing is, there's a bunch of things happening in parallel that I think really showcase that there's a lot of interest in this data collection and the usefulness that it had to so many different people across so many different disciplines, including some that maybe we didn't originally anticipate.
And how do you think about balancing the sort of more strategic approach versus the just ship it approach in terms of data preservation efforts?
Yeah, and this is a really, really difficult question to answer, in part because no two data sets or tools are created equal, and they don't serve the same universe of people. And as a result, they don't have the same sort of level of time sensitivity or urgency. They might not have the same level of this data needs to be updated over time versus, it's just historical data. And in this case, with Highfield, our experience so far is that there's kind of a mixture, if you will, of data sets that are periodically updated, especially administrative boundaries that through the Census Bureau and such. Those will get updated periodically, once a year or something like that. But then there are other kinds of data sets that might just be purely historical, at least for now. At the same time, though, some of the data sets, again, that we encounter, certain kinds of boundaries, they're not available anywhere else. And so that really, I think, motivates us to want to at least get something up there as quickly as we can, even as in parallel, we begin these tougher discussions where we, go talk to people who have used this data and talk to people who have kind of a stake in what's going on, and getting them to both provide input, to critique and suggest improvements to what we're building. A lot more work to be done on that front. And it's going to, I think, take a full community to really get there, a community-driven approach to get there.
Nice. Okay, great. Aaron, are there any other wrap-up comments that you want to make before I wrap up myself?
I think I'll plug the research showcase that is going to happen at 4 today. So make sure to come back and drop in on a few poster demos, presentations there. A lot of kind of early career, I'd say, people involved in there. And so drop by and show your support. Other than that, I think I can just hand it off to you, Amy.
Okay, great. Thank you to all of our presenters. Great, again, very energizing presentation. So thank you so much. If you are interested in continuing the conversation and be a part of the cloud computing cluster, please go ahead and join Slack, join the cloud computing channel on our Slack. Thanks so much everybody for joining, and enjoy the rest of the conference.